In this video, we're discussing z-scores. So a z-score gives you the number of standard deviations a measurement is from the mean for the data set where the measurement came from. Here's the formula then for this. To calculate a z-score for a given measurement, which we're calling x, you simply subtract the mean from the measurement, and then you divide by the standard deviation for the data set. Remember that mu is a symbol for the population mean and sigma is a symbol for the standard deviation for the population. However, oftentimes we don't have those values, so we'll just use sample estimates of those. So x bar and s can replace those values if you don't know them. All right, let's look at a simple example using male heights. So we have a measurement for a particular male, Jason's height, and they're saying he's 73 inches tall. That would be 6'1", because 72 inches would be 6 foot. 1 more inch gives you 6'1" tall. The mean for males in general in this population is 69 inches, and the standard deviation for males is 2.8 inches from the population where Jason's measurement belongs. All right, so here's the calculation. You would just plug in the numbers into their respective places. So Jason's height is our score or measurement. That's our x value, so we put it here in the first position. Then we subtract the mean for male heights, which is 69 in this case. So we do 73 minus 69, and it gives us a difference of 4. The standard deviation is placed in the denominator, and it comes over here and divides into the 4 in our last step. So 4 divided by 2.8, and you get 1.43. Notice that all of these measurements initially would have had inches as a unit. So this top number would have been 4 inches because the difference between 73 inches and 69 inches is 4 inches. But the standard deviation is also in inches, so inches over inches when you divide would cancel out, leaving you with a number at the end that has no units. That's really nice because now we just have one number, just a constant, 1.43, that represents Jason's height, right? That's really nice because all the information has been sort of condensed down into a single number that's unitless. All right, so why is that useful, right? Why are z-scores useful? So I mentioned that they are without units, and that's actually a nice feature because we don't have to deal with a cumbersome unit because sometimes units can be a pain to work with. So we get rid of them, and that's really handy. Z-scores allow us, as a result, to compare measurements from different data sets, right? Because if you get rid of the units, you can compare inches to miles if you wanted to, theoretically, right? You could also compare, IQ test scores to SAT test scores, right? Those things can be compared. You can compare boys to girls, etc. So it's nice that we can strip away the units and then have this single value that's just a number that can be compared to another number from a different data set. And then finally, z-scores provide an easy method for determining unusualness. So we're going to look at this now. How do we interpret unusualness using a z-score? All right, so here's just kind of an intuitive drawing to help you understand this. Remember that the first step to calculating a z-score is to calculate the difference between the measurement and its mean. Now, if those two values are the same, the population mean and the measurement are actually the same number. When you subtract them, you get a difference of 0. So if your height, for example, is the exact average height for the population, then you will have a z-score of 0 for your height because there will be no difference between your height and the mean for the population. So that's a very ordinary, typical value, right? As you move away from 0, you're getting difference from the mean, right? 1 here represents 1 standard deviation above average. The fact that it's positive indicates it's above average. If it had been negative, it would be 1 standard deviation below average. When you go out to 2 standard deviations above average, your z-score would be 2 as a result. And again, that would reflect that you're 2 above average because it's positive. If you were 2 standard deviations below average height, you'd have a z-score of -2. Now, from Chebyshev's theorem, we know that no matter what the distribution for the measurements you're dealing with is, or what it looks like, that will capture that range from -2 to 2 will capture at least 3/4 of the data set. So all but 25% at most will be within this blue shaded region on the number line, right? So that's a lot of data, and that's why we're calling that sort of the ordinary range, right? So 3/4 of all measurements for any data set will lie within this span in terms of z-scores. Once you get outside of that range, right? So once the absolute value of the z-score is greater than 2, so in other words, when you're below -2 or above +2, you start to become unusual as a measurement, right? The measurement starts to be unusually far from the mean for the data set. And of course, you can see the color here intensifying Obviously, the further you get from that mean of 0, the more unusual the data value is, right? The more extreme it is. So all you have to do to measure unusualness using a z-score is to look at the value that results and ask, is it something in terms of absolute value that's above 2, or is it something that's between 0 and 2? Again, we're talking about absolute value, but again, if you're talking about values that have negative signs, then of course, again, if it's below -2, it starts to become unusual. The more below -2 it is, the more unusual it is. If it's above +2, it's unusual. But again, the more above +2, the more unusual it is. I mean, you might argue that, well, for some data distributions, there might be as much as 25% of the data outside of that span. For our purposes, though, just to keep a simple rule of thumb in mind, we're going to say if your z-score is greater than +2 or less than -2, you're going to be considered to be unusual. Otherwise, you'll be considered to be ordinary, right? Some people want to know, what about a z-score of equal to 2? Well, again, these are arbitrary cutoffs in the first place, so, I won't do that to you on a test. I would never say, and I don't think any other professor would ever say, if they're using this basic rule of thumb, hey, the z-score is 2. What does that mean? I guess you could argue either way. It's right on the cusp of being unusual, and of course, it's on the cusp of being ordinary. It's a marginal case. I would say, it should be clear-cut if it's on a test, right? It should be well over 2 or well below -2, or well within the range 0 to 2 or 0 to -2. If it's in those comfortable boundaries, then you can say, okay, ordinary versus unusual, pretty clear cut. And that's probably what most of your professors would do. All right, so quickly, let's ask that question about Jason's height. Is Jason's height unusual from our last example? Well, his height had a z-score of 1.43, which falls about here on our number line, which is nicely inside the blue ordinary values range. So I would say he's certainly well above average height, right? He's more than 1 standard deviation. He's almost 1.5 standard deviations above average height, which makes him quite tall, but at the same time, he's not unusually tall, right?